Okay, so hello everyone. Welcome to episode 42 of Warsaw Quantum Computing Group meetups. Today our guest and speaker is Adam Glos, and he will give a talk, Simultaneous Resources Reduction for Quantum Optimization. So Adam, first of all, thank you for accepting our invitation. It's our pleasure to have you with us for the second time, as far as I remember, because you were also our speaker some time ago. Yeah, we are looking forward to your presentation. So this meetup is recorded as usually. This time the recording will be available a bit later because we have to wait for the publication of the results that will be published in a research article. Is this correct, Adam?
Yeah. Exactly.
Okay, great. But anyway, there will be recording from this meetup. If you have any questions, so if you have any urgent questions, you can unmute yourself, you can ask your questions, you can post your questions on our chat. So in case of urgent and important questions, we'll try to ask the questions during the lecture. So the lecture will be interactive, but if there are more general questions, we'll ask them at the end during the Q&A session. Okay, before we start, we would like to thank our strategic partners for supporting us, Snarto and Cogit, and our honorary partners for helping us in advertising this meetup. And I think we can start now. So I will now stop sharing my slides. Yeah, Adam, if you are ready, the Zoom is yours, so we can start.
Thank you very much. My name is Adam Glos. Today I will make presentation as how already mentioned, simultaneous resources reduction for quantum optimization. And actually, this is interesting that Paul mentioned my last talk in here, because I only now realized that there's actually a huge overlap between what I was talking at that time, which was Grover search algorithm, and what I will talk right now, which is optimization. Despite these algorithms are completely different, the concept underlying will be very similar. I will try to convince you to this. But anyway, let's start first with the quantum optimization algorithm. At the moment, if we think of our noisy quantum devices, there are three dominant quantum optimization algorithms. It is quantum annealing, variational quantum eigensolver, and finally, my favorite one, quantum approximate optimization algorithm. Let me just very, very briefly explain all of them. Quantum annealing relies on the Adiabatic Theorem, which says the following. If we start in the ground state of some, actually arbitrary, but for computational perspective, in a very simple Hamiltonian, and we will follow this time-dependent Hamiltonian as an evolution, then if time of the evolution is sufficiently long, we will result in the ground state of the problem Hamiltonian. The problem Hamiltonian, at least in case of the quantum annealers, right now I think it's only D-wave, is represented as an Ising model in its natural form with spins, which are variables, which can take values of -1 or 1. And from the quantum perspective, it can be a superposition of these two basic states. The problem of quantum annealing, actually there are many problems. First of all is that we actually need to describe the problem in an Ising model representation. Which one thing is that it requires a binary representation, but also that it has to be polynomial of the second order. But furthermore, in case of D-wave, we need to embed the connections which appears in this polynomial into graph which defines the interaction inside this machine. Another algorithm, which is also very interesting, is the variational quantum eigensolver. This algorithm, in principle, is not necessarily used for combinatorial optimization. Combinatorial optimization is like the classical problems like we think, like max cut, traveling salesman problem, max two or max 3 SAT, for example. It's more dedicated to the problem which has natural Hamiltonian representation. This algorithm is more dedicated to gate-based model where we specify quantum circuit called usually an ansatz, which has trainable rotation gates, usually X, Y, Z rotations, and we optimize this quantum circuit in a way such that the resulting quantum state has as small energy as possible given this Hamiltonian we try to solve. These angles, usually described as theta parameters, are optimized by the external classical procedure, for example, Nelder-Mead, LBFGS, Adam. There are many choices. What is particularly problematic about this problem is that ansatz, in principle, has no information about the problem. The only part in which we actually take the problem into account is that when we take the quantum state and compute its energy. This doesn't mean that this problem is not useful, but at least perhaps for combinatorial problems, we could expect something more. Finally, there is a quantum approximate optimization algorithm, which I will focus this whole representation, which is a mixture of these two. Again, we rely on this adiabatic theorem, but instead of following this continuous time process, we just take this mixer Hamiltonian, this simple Hamiltonian for which ground state is easy to prepare. Now, okay, this is just a product of plus states, and this objective Ising Hamiltonian, and we just apply them interchangeably. If we do this in a Trotter way, meaning that this Pi and Ri times angles are very, very small, and this K is sufficiently large, then it is actually promised that there is such configuration of these times that will get the optimal solution at the end. Usually people hope that there is actually something more behind this algorithm, that we don't really need to take Pi, Ri really small. And again, we just optimize this Pi and Ri with some external classical optimization algorithm. This is already in some sense better than Warsaw Quantum Eigensolver, because right now our quantum circuit actually has some information about the Hamiltonian. However, there is a problem. Problems we are trying to solve are usually quite complicated. This affects the number of resources we need to from the quantum hardware so that we can run this algorithm. How and if can we minimize these resources we need? So to answer that, let us first consider what kind of resources do we actually need. In the scope of this presentation, I will focus on all the ones I listed in here. I will explain them in detail in a minute. Let me just quickly mention that this is a list developed by me and my team, Ozem, Zotam, and Bencha. But actually claim that at least from the QA perspective, this may be the complete list of all simple to obtain quality measures. What I mean by simple to obtain, then this I will try to explain actually at the end of the presentation. But anyway, let's go into this. I will try to explain all of these quality measures one by one from the perspective of max k-cut problem. Max k-cut problem goes as follows. We are given a graph and we are allowed to use k colors. Suppose we have 3 colors at this moment. Our task is to color all the nodes, attach color to each node in such a way that the number of edges connecting different colors is maximized. For example, this edge we include in our sum, which we want to maximize because it's connecting blue and green color. But if this would be blue, then we would not be allowed to do this. There are two similar problems which are maybe a little bit wider considered in the literature. There's max cut problem, which is a special version where we are allowed only to use two colors. And there's graph coloring, which has more than two colors usually, but here the problem is that we actually need to find the coloring, whether it exists, such that all edges are connecting different colors. But we'll see to this max k-cut where we are trying to maximize the number of edges. So how can we describe this problem as an Ising model? Usually what we do is that we are looking for a cubo model. Cubo model is in such a sense that while spins can get values can have values -1 or 1, beats can have values 0 and 1. There's extremely simple transformation which can map one to another. So let us just I will show this in a minute. So let us just stick to this representation with bits. If BTI would mean that a node T should have color I, then it means that this cubo would exactly explain the would exactly give the max k-cut formulation. There's only a small detail done. Excuse me, I noticed that I took the wrong formulation. This should be sum of I different by j b t I b t j. So you can notice the following: if I, j are different, and node T is colored with color I, and node T prime with J, then we are considering this edge, because only in that case we'll have 1 in here. What is more important in context of this presentation is this part, because we cannot allow that node can have more than 1 color or 0 colors. We actually need to make sure that the sum of all these bits equals 1. So there's exactly 1 color chosen for this representation. With appropriate constant, which needs to be sufficiently big, this will be equivalent to the original max k-cut problem. So let us analyze this a little bit. We have n times k qubits, but the thing is that we actually, I noticed that I took it from TSP, so maybe I shouldn't do this before. But the thing is that what we are actually interested is that we are interested in the following states. So for 3 colors, we could say that here we choose color 3, here we choose color 2, here again we choose color 3. Even if we choose more colors, then what you would have is that only single one is allowed in this representation. For TSP, this gives us n to the n possible solution. For max k-cut, we need k to the n, because for each of n nodes, we need to attach 1 of k colors. However, if you would choose appropriate mixer is simple to prepare Hamiltonian. which is called XY mixer, we can actually make sure that we are not considering all possible solutions. So here, any number of ones could appear here, but only the one which we actually want. This squeezes the number of the set of solutions from 2 to the k to the n, which was before, because we have k and bits, each can have 0, 1 value, into into k to the n. But these values are really large, so actually it is better to take logarithm of these two. So logarithm of this would be k times n, and here it would be n log k for max k cut. Just mention, our representation still needs n to the n times k qubits. But what we do is we are dropping this mixer, this part of the Hamiltonian. We slightly change the initial state, and thanks to this, we are living in a smaller part of this Hilbert space, spanned only by the valid solutions. So the thing is, how small the number of qubits and the effective space size defined as the logarithm of the states we are evolving, how small it can be. This can be lower bounded by the logarithm of the number of solutions, because each computational basis state is a different solution. Therefore, we shouldn't be able to go beyond this value. In case of max k-cut, both this qubits, number of qubits and the effective space size will be n log k. Another very important quality measure is the number of gates. In the case of QAA, what we usually implement is we implement Z interactions, meaning that we have some number of qubits, and all of them we are implementing this kind of Hamiltonian. This interaction, here's an example for 3 Zs, can be decomposed like this. So we have a layer of CNOTs, single rotation Z gate, and then the same CNOTs but in the inverse order. There's also one aspect that it is sometimes interesting to count also the trainable gates. This is because the number of these parameterized gates may affect the cost of gradient estimation. I don't want to go really into detail from this perspective, so I would just let's just remember that gates, we want to reduce number of them because they introduce noise, and this is a very important thing. The smaller is the number of gates, the more coherent, the most trustable the quantum evolution can be. Suppose we take max k-cut problem again. The question is, what is the minimal number of gates we would need for this problem? This is not a very simple question. Our lower bound was, in the case of max k-cut, n squared, which is actually the number of degrees of freedom. What I mean here, max k-cut problem is specified by essentially by the graph. Once we know graph, we know the problem. Graph has around n squared edges, and the fact whether this edge is or not in the graph is our degree of the freedom of the input problem. Since we want to input this information into the quantum circuit, what we are assuming that each degree of freedom would require at the very least one gate. This is how we derive that number of gates and parameterized gates needs to be at least n squared. Finally, if your quantum hardware can implement gates in parallel, then we have another factor which is called a depth. Let us just take a little look at this circuit. You can see that all these gates are applied on independent qubits. Not all machines can do this, but in particular, IBM machines can implement all of these gates in parallel. This way, if we, for example, have n-squared gates, n qubits, then we can implement n gates at once, which means that if we would lower bound, if we say that we have n-squared gates to implement, then at best we need n-squared over n log k, number of such steps with multiple tasks, multiple gates implemented at the same time, which is also good for us, because the longer we are trying to keep quantum state coherent, then actually the most likely we will fail. Actually, there's a very famous paper which shows that with increased depth, we are observing the effect called barren plateau, that it's actually very, very difficult to optimize similar quantum circuit. What is very important here, that here, one qubit gates are quite simple to implement simultaneously. It is less trivial for the 2 qubit gates. If all qubits can interact in pairs simultaneously, then basically what we just want to do is to maximize number of pairs of qubits on which we simultaneously are implementing the these 2 qubit gates. For example, here we implement between 2, 3, between 4, 5, between 6, 7, and between 1, 8. This is completely possible. But not all quantum machines can follow this all-to-all topology. In fact, some machines are more restricted, and you could say the reasonable worst-case scenario is when qubits are arranged in a line, and only the neighboring qubits allows us to give some interactions. In this case, for example, we wouldn't be able to implement this layer on linear nearest neighbor because the first and the last node are not connected in here. Here we will need to apply something which is called swap network. I again don't want to go into details. Anyway, this may be more complicated. In our case, we consider both of these. The lower bound is the same because we didn't assume any kind of connectivity issues here. Although it may be that LNN would be much more difficult, likely it would be much more difficult to achieve this optimal solution for LNN than for all-to-all. Finally, the very last quality measure is the number of measurements. Here, actually, we don't really have issues with the coherence of the quantum state, with the quality of the solution, but with the quality of estimation of the energy of the quantum state. The thing is that physically, we will not have the whole description of the quantum state, but we only get samples of this, like the sequence of zeros and ones. Based on this, and given our Hamiltonian, we can compute the solution value, usually called energy in this community, which finally, after doing many statistics, this will give us the expected energy of the quantum state. This is how it's called. If you want to have this estimation with precision epsilon, then the most state-of-the-art form taken from variational quantum Eigen solver is given this Hamiltonian with such parameters. We should take this number of measurements. This formula is taken that actually we are estimating the energy given each of these Hamiltonian terms independently. So this should be small I in here. And run sufficiently many circuits for them. Then estimate energy for each term, and finally compute the wave sum out of it. However, for QA for combinatorial problems actually in general, there's a better method, which is simply a simple application of the Hefting theorem. In here, what we need to know is the difference between maximum minimum energy. Actually, it's upper bound on this difference. And we could taking fixed p as fixed small value, we can have quite similar expression. Just instead of this squared L1 norm, we'll have square of this difference between max and min. Apparently, this estimation is not worse than the one drawn from the state-of-the-art Warsaw Quantum Eigensolver method. What is the minimum number of energy estimation precision we want to have? This depends obviously on the epsilon, but assuming that we only require fixed precision, then what we actually need to take into account is the difference between smallest and largest possible solution value, objective value of the function we want to optimize. In case of max cut, this depends on the number of edges, but at the worst case scenario, we will have n squared number of edges included. This is the maximum value. The smallest is 0. So we could say that the energy span, which is basically the main factor we will consider, is again lower bounded by n squared. And these are all the quality measures we'll consider. And now, what is the problem? Theoretically, what you could expect is that if you have a function which is easy to compute on the classical computer, on your notebook, for example, on your phone, then it should be also simple to implement this on the quantum circuit, which we will expect for QA. So let us take this very simple function, which is minus product of n bits. This is actually, so this is minus n operation. Following this transformation, this is a transformation which maps this binary 0-1 value model to Ising model, we'll obtain the following Hamiltonian. Now, the most standard way of implementing is that we expand this polynomial, so that is just sum of polynomial expressed terms, and we implement each term separately. However, you can see that if we would do this in here, then except of this very tiny exponentially factor, which actually can be omitted because it's just a scaling, but here we have 2 to the n terms. Now, in general, we cannot expect that that big size circuits could be implemented in the near future. Actually, even if it would, if in our case, if we have that big circuit, then likely there are some classical methods which are better or give similar quality, and we don't have to care about the effect of noise. So you could consider this as an example where classical function, where the function is classically very simple to compute, because well, this is easy implemented in any language like Python or C++. But using the state-of-the-art method of implementing this into quantum circuit, it becomes really, really difficult. So apparently, as maybe some of you would expect this, there is a better solution, and this is the part which is similar to what was my presentation last time. I think 2.5 years ago. I don't know when it was exactly. Is that because this is AND operation, what we can just do is that we can apply generalized control not operation with target on extra qubit, apply rotation Z, which will give a local phase, a rotation in Z basis on this ancillary qubit, and then uncompute this. Why this is similar? Because this is exactly how the problems are encoded into Grover algorithm, which was exactly my presentation. Now the thing is to use this trick not only for the Grover algorithm, but actually for QAA, which I'll call from now SimQAA. Without going to details, by the way, this can be implemented in ON squared gates. In fact, with Ancilla, we can even reduce this to ON gates. So, choice between 2 to the n and ON is, well, it's a simple choice. So, let us go back to max k cut. Again, graph is an input, we have k colors, we want to maximize number of edges connecting different nodes. As we mentioned before, now number of qubits and the effective space size is logarithm of k to the n, which gives the following value, because it's at least number of solutions. Number of gates, number of parameterized gates is at least n squared, because this is how many degrees of freedom we have for this problem. Depth coming from dividing number of gates over number of qubits is like n over log k. Well, this is suspicious, but let's just take it that this dividing over log k, but let's just take it without thinking about it a bit. And then there's an energy span which is related to number of measurements. So we took, if not all, at least the most popular represent encodings of the max k cut with different options. Some of them have the most traditional mixer with X rotation. Some of them has more complicated like XY. There is Hobo, which uses higher order terms in the polynomial than 2. And finally, there is Fuchs QA, which I will explain in a minute. And what is the problem with this representation? Well, one of these problems is that they will not match the optimal values, these lower bounds we derived, I'm not claiming at this moment that this is possible. It may not be achievable. But also what we could say is that for all of these encodings, at least 3 quality measures depend significantly on k, meaning that there is polynomial, n-dependent polynomial, number of node dependent polynomial on n, actually which matches these optimal values, but times polynomial depending on k. So overall, this quantum circuit, in some sense, at least in number of gates, will significantly grows with both number of qubits and both number of nodes and number of colors. So actually, I could spend a lot of time explaining each of those 4 algorithms, but let us focus on this Fuchs, because this is particularly interesting one. In here, first thing what authors did is that instead of having 100 representation, they simply take the most standard binary representation. For example, 0, 0, 0, 0 goes to 0, 0. 0, 1, right? 0, 0, 1, 0 goes to 1. 0, 1, 0, 0 goes to 2 in binary, and 1, 0, 0, 0 goes to 1, 1. From this, you may have noticed that while this requires k qubits per node, this will only require log k. So this way they managed to drop the number of qubits required from n times k to n log k. Well, because number of qubits was reduced, and also the effective space size was also reduced, right? Because subspace, Hilbert subspace cannot be larger than the full Hilbert space. What they didn't do very well is that they started in superposition of all binary binary sequences, meaning that, for example, if we would have only k equals 3 colors, then we still would start in superposition of these 4 values, but the meaning would be color 1, 2, 3, and 3. Those relatively complicated explanation on how they derive this quantum circuit, although very interesting one, I must say. However, in essence, it could be explained as follows. First, we give a reward every time the colors are different, but actually not colors, but this binary string. And then, if this binary string actually were denoting the same color, like this 2 and 3 in binary, then we're taking back this reward. And this is what was particularly costly, because for all this unnecessary binary representation, which were describing the single last color, for all these pairs, we needed to apply these fixes. In particular, here it is for 2, 3, 3, 2. This results, this results equally high cost, which I can actually even visualize right now. So this is number of gates, depth, and depth of NLN. These are actually 4 algorithms, one which I haven't explained yet, and this violet one is Fuchs. Notice there's a logarithmic axis, y-axis, so the cost grows significantly with the number of colors. But then what we did is that instead of starting of superposition of all these 0, 0, 0, 1, 1, 0, 1, 1, we simply start in a superposition of one binary string per color. So we were ignoring, we were basically ignoring this situation. Then we needed to choose appropriate mixer which would preserve within this subspace. But finally, it gives us very, very efficiently implementation, which is actually not only better up to polylogarithmic factors than all the one I introduced before, but in fact, up to these polylogarithmic factors, it matches the optimal values we were deriving, these bounds we were deriving before. The whole idea, and it's exactly as in Grover's search, we are designing the pseudocode which computes the part of the whole objective function. Then we transform this objective function into the quantum circuit as in Grover. And if we have this one ancilla qubit which is set to 1 only in the cases which are interesting for 1, we apply the Z rotation. And then we do the uncomputation. Not only this representation is better in the quality measures we considered, but also in a sense it is simpler, because we don't really need to design the model and the QUBO model, the IZIM model. If needed, we don't need to, depending on the problem, we don't need to make a quadratization, which is reducing the order of this polynomial we have. We just design quantum pseudocode. Ideally, we have a kind of automatic way of transforming this into quantum circuit. Silk, language Silk SILQ seems to be a good candidate for this, and we already have it. Finally, you could notice which is actually kind of repeated, that the dependency on k is dropped. We have only polylogarithmic dependencies in here. So what are the numerical effects of this? Well, this was the plot which was supposed to convince you that the Fuchs QA is not a really good design for large number of colors. It is quite good, however, if the number of colors is power of 2. This I must honestly say. However, let us just remove this Fuchs QA from the plot so that we could see what's happening for the other elements. We can see that here this green line is the one which was developed by us. You can see that X query and XY query has a very high demand on the number of qubits. And at some point, also for the other metrics, other max k-cut variants becomes more and more costly. For example, depth on linear nearest neighbor for around, let's say, 45 nodes, our method has superior depth over the other, compared to other. Similar for gaze. Here we could say it for even around, let's say, 20 colors. The only factor in which we are worst is the regular depth on all-to-all connectivity, where you can apply signal between any pair of gates. However, this also complies with the table I showed, because the depth for X query and XY query is n, and here we have this log k factor. So it will be actually problematic at some point. However, I must also say that this all-to-all architecture, where we could apply gates in parallel, at least I am not aware of any quantum hardware which has these two properties simultaneously. Maybe they will appear. Personally, I believe there is some fundamental issue with controlling the quantum system, which will prohibit us from doing this, from having these two properties. So maybe this is the very strange way of showing my results to answer whether this was interesting. Well, it was very interesting for many reasons. We reached optimal quality measures, all we consider and all which I claim are important, at least from those simple to compute. We essentially dropped the dependency on k. We have only these polylogarithmic factors, which hardly matters. Therefore, it fits very well the NISQ requirements, the requirements from the noise intermediary scale quantum era, because all of these factors actually matter. Finally, this max cut problem is actually a very important optimization problem, which has some serious applications. So probably you expect an answer no, which actually there is. The problem is why we maybe not dislike this problem, but we're not satisfied with what we have, is that actually we took very, very simple problem. We basically took this Fuchs cube away, added a different interpretation of this quantum circuit, choose better initial state and mixer, and removed all of these redundant fixes circuits. And basically, that's all. This is how we obtained our solution. But then let's go with another problem, traveling salesman problem, which is apparently a much harder problem. The traveling salesman problem is a problem in which we have a bunch of cities, and we want to find a closed road which passes through all the cities exactly once. This has a nice cubo representation taken from Lucas' famous paper. It was, I think, formulations, cubo formulations, excuse me, I think Ising models for many NP problems. Why this is very good for quantum annealers? it could be much improved a lot for QAOA. But let's go with this example. In this example, again, we are having one hot representation. If we have a black square, which is bit equals to 1, each square is another a single bit. If this bit is equal to 1 in the second row, third column, then it means that in the second time, we are visiting city 3. So in city 1, we visit city 1, in time 2, we visit city 3, in time 3, we visit city 6, in time 4, finally, we visit city 2, etc. However, the thing is, between these two times, all possible edges can appear, right? Between 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, to 1, to 3, to 4, to 5, to 6, etc. This means that when we will design this problem, we need to include the whole cost matrix only for those two quantum registers. But this is just between time 1 and time 2. We need to do the same for time 2, time 3, time 3, time 4. And finally, it appears that we need to repeat this cost matrix, which has n squared degrees of freedom, because there are that many pages of cities, n times. Those, because of this, we artificially increase the number of n degrees of freedom from n squared, which is the true one, to n cubed. And this is the fundamental reason why many of the models were not able to go below n cubed number of gates. There's actually one exception, which is this Miller-Tucker-Zemlin integer linear program implementation. They also couldn't achieve this n squared optimal value. Also, they also have n cube, but actually here the reason is a different one. And the reason why this argument doesn't work is because they don't have time to city representation, but city to city. Anyway, this n cubed number of gates, as far as we know, was not beaten before. And actually, many of other quality measures were also not, in many cases, not even close to the optimal values. For example, here you can see that depth for all of these representations is n squared for a linear nearest neighbor connectivity. So like this line connectivity. So what we did is we started in the superposition similar as in max K-cut, meaning that we have this binary representation of the city visited in given time. So here for 6 cities we have only 3 bits for binary representation. Thanks to this, we were always guaranteeing that each time we visit at most exactly one city. Sorry. But what we need to assure is that cities visited is exactly 1, which means that for any pair of time points, the city visits are different. Finally, despite we are working on time to city representation, we're actually creating node-to-node representation, like in this ILP. So from this node to go to this node, then from this one goes to next one, etc. We choose a relatively advanced Grover mixer. This mixer works like this, that we apply inverse of the initial state preparation, multi-control Z rotation, and then again unitary applying the creating the uniform superposition. And again, these Hamiltonians were actually implemented through a pseudocode than than by explicitly presenting this Ising model. The pseudocode looks like this. I don't really want to go into details inside because I already took like 47 minutes. But if there will be time later, we can go back to this part of the presentation if there will be interest. But in the essence, we achieved the following. First of all, our model is again the best, meaning that for all of this, compared to each of this model, our quality measures are the same up to polylogarithmic factors or better. But again, what we achieved is that these SIM2A values up to polylogarithmic factors again match the optimal bounds, the bounds which we derived for this DSP. Here, maybe I should quickly mention this. We have n log n effective space size and number of qubits because we have n factorial solutions, all possible permutations. We have n squared number of gates because we have that many degrees of freedom, the cost matrix. Depth again is taken from dividing number of gates over the number of qubits. And energy span, here we took assumption that the cost matrix has bounded elements. So the longest route, also all routes are positive, and the longest is at most n times maximum value of this cost matrix, which gives us this n factor. But okay, and now is what I told you that I considered with my team all quality measures which are simple to derive, which are not simple to derive. So there are two which comes to my mind, so very important one actually. One is how easy it is to optimize this quantum circuit, because remember that both in QAOA, these parameters we have are optimized by external classical optimizer. And secondly, what about noise robustness of this quantum circuit? How destructive will this quantum circuit will be the effect of the noise on this particular quantum circuit? Unfortunately, I don't have results for the second one because these problems, these constraint problems, becomes really big at some point. But I was able to at least quantify how it is simple to optimize the quantum circuit. Here I considered QBO, HOBO, two variants of our implemented method because we can choose different mixers, and the XY with the complete mixer, meaning that we apply XY Hamiltonians between for all pair of qubits. Sorry. So taking the red line, which is our implementation, we can see that among all of those we have, depending on the metrics, depending on the number of cities, our method is better or of similar quality. So actually, these samples are very small. We cannot honestly say that for a large number of cities, our model will be better than any of those we consider so far. We have in this plot. We cannot honestly say this, but based on this, we will. I believe we can also say that our method will not be significantly worse than the other considered. And taking into account we don't need that many resources from the quantum hardware, I would say that in this sense our method is superior. And unfortunately, this superior is too big word because GMQAOA, a special variant, is simply the best. The reason why it is not on the plot is not because we are not able to compute it. It's quite the opposite. Its optimization was extremely hard, but this method was so good. It was so good that simply all these lines in here will look almost flat. This will be basically non-distinguishable. However, it comes at a price. With price, GMQA has simply terrible quality measures. It needs n squared qubits, even on all-to-all connectivity. It has n squared depth. It has n to the 3 number of gates. Fortunately, at least energy span and the space size is big, but actually, these first 4 are the most significant ones. From the perspective of the current hardware, because if you will not have hardware which will run this method with these requirements, then basically we don't care about the energy span of FFT space, because this is kind of only quantum advantage issue, not possibility of running this. So we're not going to say that our GMQA is absolutely the best, but it's the best of those we could expect to be run in the nearest future. Finally, this was all about traveling system problems. So what about its generalization? Well, we're considering different problems. In particular, we consider set cover problem, which was relatively simple to implement. We also considered integer linear problem in general and graph isomorphism in general. Unfortunately, we're able to provide some trade-off methods using our SimQA array. However, trade-offs of it is between depth and number of qubits is the best thing we could achieve. In particular, graph isomorphism is, I could say, the simplest problem to consider, for which we were not able to provide implementation. We achieved both optimal number of qubits and optimal depth. I'm not saying it is not possible, but anyway, we need to keep in mind that there may be such complicated problems for which simultaneously optimized quantum circuit, the sense of the resources needed, simply do not exist. And at best, such trade-offs will be achievable. This is all I wanted to say today. Hopefully you found this presentation interesting. If there are any questions, I would be happy to answer them. Unfortunately, I cannot say that this will be on archive soon, because we are still finalizing a few details related to this.
Okay.
So this will be like some hopefully nearest future.
Okay, good, great. Thank you, Adam. Do we have any questions to Adam? I don't see any questions on our chat. So let me maybe ask the first question. So it will be quite a general question, but I believe it might be quite educative at the same time. So you have this different metrics or quality measures, let's say like number of qubits, depth, and so on. Could you maybe elaborate a bit on which of these metrics are most important, and what are the impacts of the of these metrics on, let's say, efficiency, like in terms of time of computations or cost, and so on?
There are two aspects I would be which we should consider each metrics. First aspect is whether the more pessimistic the value is, the biggest usually, I think. Yes, the biggest the value is, the less likely we will have the quantum hardware, which will be for which it will be possible to run this algorithm. And this is the first question about the possibility. Second thing is, if we have the quantum hardware for which we can run this algorithm, how simple it will be to optimize the quantum circuit, and by this, how likely it will be to have quantum advantage because of this. So, number of physical qubits, number of gates, yes, you could say this, and depths are about possibility. The bigger these values will be, the less likely the hardware will exist which will run this algorithm. On the other hand, effective space size, number of parameterized gates, here I'm not exactly sure about this. This is more tricky than it sounds. And energy span is about quantum advantage. The smaller this value will be, the more likely we can expect some good, the more the easier it will be to obtain quantum advantage. And this is quite relatively simple and straightforward. Number of it is overall quite difficult to construct big quantum hardware. Even the biggest hardware, I think, have between 100 and 300 qubits after all these years. And all these four factors anyway contributes to the noise. More gates means more noise. More bigger depth means larger decoherence. It's less clear for number of physical qubits, but there are also something which is a type of noise which is called, I think, crosstalk. The way I understood it so far is that despite we don't do anything on this qubit, but on another qubits, then this control on the other qubits affects this all the qubits, all the neighboring qubits. On the other hand, this effective space size you could consider as number of solutions. The smaller number of solutions, then usually you could expect, the easier it will be to find the optimal solution among them. Number of parameterized gates indirectly, unfortunately, impacts the number of measurements you need to estimate the gradient for the quantum circuit. Finally, energy span. The size, how many measurements you need to compute, just both for gradient estimation and just energy estimation. And I'm not sure if it was the full answer.
I think it was very good and detailed. So thanks, Adam, for this. All right, I think I still don't see more questions on our chat. So Adam, I remember that there was a part with the code that you potentially wanted or was ready to were ready to present if we have time. So it's after 7 p.m. now in Warsaw, but it's fine to come back to this part if you think that it might be interesting, because I personally believe that it might be interesting for if not our participants, that people watching the recording later.
So I can explain them because these are mostly classical algorithms, pseudocodes, in fact.
Okay.
How to implement this in quantum circuit is a little bit more difficult. But if a person is skilled, for example, took part in the IBM quantum challenges, which were explaining the Grover search algorithm, then it's likely that they will see how to do this. And again, a little bit more advanced question is how to do this with small number of resources needed. I will try to get to the first level, meaning understanding the pseudocodes. Basically, we need to check whether the quantum registers form a permutation, and we need to implement the codes of the root. So if we have list of numbers, how to verify whether they form a permutation? We simply need to check whether each number occurs exactly once. And this is exactly what we are doing. We are making counting registers, which are by default set to 0. And then for each time and for each city, if at time t we are at the city I, then we simply increment this counter by 1. Once we do this for all such pairs, which can be done efficiently by something called swap network. I don't really want to go into details right now. What we need to do is that we simply should check whether all these counting registers are set to 1. If this is not true, then we set flag 1 to flag qubit to 1, otherwise to 0. Then once we get this flag in quantum system, it will be done in superposition. We apply the rotation Z gate with trainable parameter theta and penalty value A. This penalty value is the same as we have here, and it overall quite frequently appears in this kind of binary optimization. And after we apply the rotation with that, we just uncompute flag, which is basically we implement all of this just backwards. We apply inverse of this unitary map. In classical pseudocode, it is not very clear because in classical program, not all maps are reversible. However, once we create the quantum circuit out of it, then this unitary which implements this flag, which computes this flag, well, it needs to be reversible because this is how quantum computing works. Slightly more complicated is about implementing the cost route, which is basically this part. So if at time t we are at city I and t plus 1 we are at city j, then we add this cost wij. The big picture is that we are transforming the time to city representation into city to city. By city to city mean that in IF, if at IF quantum register we have value j, then it means that we have the step from ICT to j. And know that if we have already specified IF register, it means that we have only n minus 1 actually possibilities where we can go. So here we need only n degrees of freedom. And this where we avoided this artificial redundancy we were producing for time to city. So we are transforming this representation from time to city to city to city. We implement on each city to city register this cost matrix. And finally, we were again uncomputing everything. And this is very briefly explained here. EI are this city to city, meaning from city I go to city, whatever is the value here. FI are just ancilla qubits for us to help. If in this ancilla we store the value that at the register for time t, which are a city I, then at register from city I, we store the value of bt plus 1. This may look overcomplicated, but it is better. It was better to write it this way because of how to make it efficiently. And finally, once we create this representation, which is always valid if the quantum register is a permutation, then for each register EI, which we have this loop for over I, if the value in this register is j, we implement this wij cost again through rotation map. Yes, it was complicated. Sorry, it would be perhaps much easier if it would be a text to be read. But...
Okay, but anyway, thanks for your explanation. There was a question on our chat. If there is any material that you can share with us about your work. So I know that so you are also waiting for publication on archive, but maybe you have some older works that you could share at the moment.
Well, there is a only similar work, which is exactly this Fuchs QA implementation. This is how we call this, based on, after the first author, which is efficient encoding of the words max KCAT on quantum computer QA. This is this bad implementation of max KCAT, but in principle, it is exactly doing what we are doing. Simply, they took it from, I would say, a bad perspective. Also, there's an algorithm which is called Grover adaptive search, I think. And this is again different algorithm, but they also have this concept of implementing an oracle. However, they have like different QA way, and also I would say they make a strange thing that anyway they required the, I think it was quadratic integer program, but you could say, for let's keep it simple for now, that kind of a cubo, but with integers, not only bits, as an input. So I would say it was slightly overcomplicated from their perspective. So not exactly, but there was something around. It was in concept. It is. If you look at many papers in the concept, it would be not that straightforward. Actually, I was a little bit surprised that no one has came out with this idea.
Okay, yeah, that's nice. So anyway, thanks for that. And yeah, so as Adam said, his paper will be available on archive soon. So hopefully this year, in a couple of months. And then we'll also publish the recording. All right, any more questions? Last chance to ask some questions. I don't see more questions on our chat. So Adam, thank you once again, and Maya also.
Thank you very much.
Thank you on our chat. So let's now stop sharing, and I will just share my slides for the last time, and we'll finish. So yes, so this was episode 42. We would like to thank once again our strategic partners, Naruto and Kogit, and our honorary partners. And regarding the next meeting, we are not sure yet. It's possible that, so for sure we'll do a summer break. So most likely there will be no events in June, July, August, and September. It is possible that we'll try to organize maybe one more event at the beginning of July, maybe one in September. But by default, as for now, what we can confirm is that we'll be back in October, at the beginning of October. But anyway, please follow our websites, fan pages, channels, profiles, join our group or mailing lists to stay up to date, and then for sure you'll be noticed about our future events. So we hope that you enjoyed this event. I will send you the feedback form later today, and as we said, the video will be later available on our YouTube channel, but after the publication is out. So thanks, Adam, once again for a great presentation. I would also like to thank all the attendees for participation. Just in case, if it turns out that it was the last meeting of Warsaw Quantum Computing Group before the summer, I wish you a great summer, a great holidays, and hope to see you next time on during our future events. Thank you. I will now stop recording.